Hey guys, here we are back again for some more optimal start mathematics in our building automation systems. We've been talking about this a lot. We're studying mechanical engineering theory on how to optimally start HVAC systems based on research. So that's in the research paper directory by PNNL. They define a couple different mathematical models that you can run that predict minutes to warm up or cool a zone before the building is occupied, and we feed in zone temperature, set point, sometimes outside air temperature, and when the schedule is for the building is set to start. These are different models we're studying. We did model 0, which is the typical degree per minute model. The quadratic recovery model based on the delta temperature, model 2, which is the model 0 plus the weather ratio, and then model 3, which is the multiple regression. In our last couple set of bonus days, we were looking at doing multiple regression manually, the math behind it, using matrix algebra, transposing matrices, and doing some of the math behind it. And then this one, the next set of bonus days for our AI created lesson plan, is some of the first order models that are, it's an iterative model, some calculus behind the scenes going on. So then it's taking the log of some of these alpha A, alpha B, alpha C, and so we're looking at this in a little bit more detail. And so we're going to go right into our lesson plan. All of this was created by ChatGPT. So in our lessons, definitely read the paper. So this has been my special interest for about a year now, is kind of diving into this, because it is probably the most easiest low-hanging fruit of an energy saving strategy for a building, but it's just never implemented in the real world in the building automation systems. It's very complex to get it right, and quite often it's just never implemented at all by contractors that set up building automation systems. And then some of the optimization contractors, like myself, will try and enhance the building automation system. So it's still a work in progress, and AI can help us a little bit. Okay, so we're on bonus day 12, which is here for model 4. And I just realized I didn't start VS Code up yet. So let me just get into our math lesson script. Here's VS Code. Okay, open up our terminal. I'm in Windows and PowerShell. Some of the earliest videos we walk through how to download Python and get it set up. Feel free to reach out to me on LinkedIn if you need assistance. Okay, so this was our math lesson that we studied yesterday in implementing this estimate of least squares. So this was part of the code that we, through this iteration of the data, it's like attempting to calculate an error, basically. So it's just trying to calculate a percentage of error over each iteration. So that's what we were looking at yesterday. Let's see what today is. So compute model 4 T optimal. So that would be minutes is our T value from a real startup window. Goal from a short after startup window, estimate C, then compute T optimized. Model 4 uses the formula log of parameters A divided by B divided by the log of parameter C, alpha C, deadband, initial error, and learned decay ratio. So I think initial error, that was our delta temperature between our zone temperature and the zone set point. So the minimal data you need is temperature set point and the temperature of the zone. Each sample, I guess on a 1 minute interval. To convert to errors, so this is just saying to get our heating error, it's just our zone set point minus our zone temp, and then if we're in a cooling application, it would be our zone temp minus our set point. I think you could even just take the absolute value. So our B parameters, our initial error, estimate C, choose the deadband, and then compute. Okay, so here we go. We got some more things to play around with. So, what we did yesterday is we took these, so the AI generated lessons, like it created these helper functions and kind of hid the code to make this kind of clean and easy. But I kind of found it nice to actually kind of look at the code. I guess it wasn't too scary. So I think it's in the scripts directory, helpers. Let's see. So I think we wanted estimate least squares and model T optimal minutes. Okay, so these are our helper functions that, and then I found it kind of nice to just perhaps look at some of this code. Okay, so it's looking for something clamp and safe log. What was clamp? Looks like some more functions here. Sorry. Hopefully this won't be too bad. And then I bet import a math library and typing library, I guess. I bet this is from typing import list. These are just data types, data structures, I guess. Not really sure why this is needed, but let's see what it does now. Looks like it still runs. So if we do our mini lesson, I'm just going to copy this code because we already maybe I'll just comment this out. That was yesterday's code. Okay, so we're getting a value of C. All right, so we have a temperature deadband we talked about the last couple of days. That's just, so if our set point is in Fahrenheit, 72 degrees is pretty typical for a zone set point. If we have a deadband of 0.5, I think that's only a quarter of a degree up and down. So that is very small. Typically the deadband would be, that I see is 4 degrees Fahrenheit, and that would be 2 degrees up and down. So this should be not very realistic in the real world, but some contractors trying to implement this stuff, you'd be amazed. Usually it's by technicians that maybe they don't have a very in-depth mechanical engineering background at all. Some technicians could be an IT background person or an electrical installer, so they might be really sharp at troubleshooting, you know, with the trade that they came from, troubleshooting shorts and sensor wiring and relay logic or networking on the IT LAN. But then when it comes to implementing, understanding mechanical engineering theory, you know, they might be trying to just fix something. So I see it all the time. All right, so our code runs. We can kind of see like what this does. It's so this is our that's our equation. So if you would go into, you could even see this in the paper. So if you would go see this in the paper, model 4, here we go. Here's our model. So, and then it talks a little bit about how that first order physics driven. It's a simple first order model to predict response time. Simple. Okay, so where were we? So try a deadband of 1 instead of 0.25. So if we had a deadband of half a degree, that gave us 21 minutes. And let's try a value of 4. Three and a half minutes. So that's something we did on previous exercises, is that the bigger the deadband, in theory, the less the HVAC system has to run to reach that condition of meeting temperature set point. So I think that's what it's trying to prove. Seems about right. The thing that is kind of confusing to me is this C parameter. So this is the part that's a little confusing to me. It's I think like what this is would be the errors, like errors is our temperature set point minus our difference between temperature set point and the zone temp. So this would be if the optimal start runs once a day, this would be a day of data. Previous day's data, that day, and this C parameter is still kind of a little bit of a mystery to me, but we've been talking about it, so that what it does is that it iterates over it's a iteration process, and it tries to compute that this is optimized value. So it's still kind of interesting. I have to let that soak in a little bit more. But the last couple math lessons, we talked about when this number is very high, closer to a value of 1.0, that it's not doing anything basically. And then if it's low, in between 0.5 and 1, that there's like lots of convergence going on. Try a bad day where the errors barely change. Try a bad day where the errors barely change. I wonder what that means. A bad day. I don't know what that means. So let's just try. We did this yesterday. Just throw some wildly high number in there. And yeah, this number, it gets really off. So and if we tried 6.0, I think it's asking like if this barely changes at all. What happens to our C value then? That's a perfect 1. It's kind of interesting. So that's Try a bad day where errors barely change. What does the model predict? If C is estimated too high, closer to 1, does the time shrink or grow? Oh wow, it explodes. So yeah, it's predicting 405,464 minutes. So that's a lot of minutes. Yeah, this is kind of interesting. So model 4 is learn decay, then solve time to deadband. Pretty interesting. I'm almost kind of curious to ask AI a little bit about this. So we were on, sorry guys, I think this was day 12. Day 12. Where were we here? So we were on day 12. Might as well give it the paper again for some context. So these questions, are confusing. I'm just gonna say could this be bad days? I don't get the question. Would that mean that there was 6.0 temp delta for each day that the optimal start ran? Why would that be bad? It causes, which blows up the minutes calculation. To me, it seems like if in theory, if the weather was the same and same patterns for the HVAC system or whatever, why couldn't the runs per day be the same? The HVAC took the same amount of time to run each optimal start run. Whatever. I think it'll understand. Okay, so it's reading. This is a really good question. Confusing. So a bad day, what the error, where errors barely change mean when the paper in your exercise said try a bad day, barely change. It does not mean the same weather, same optimal start time, and same algorithm. It means the specific situation during startup window. When the rooftop unit turns on, the zone temperature does not improve, barely improve. So your example, interpretation at minute 0. Oh, I get it. So this is, these are not runs per day. This is per minute of the same run. Okay, so I thought that wrong. The system is running, but the building's not responding. Okay, so okay, so that was my mistake. I guess we learned system, so that makes sense. So that's why there's 0 decay. And then when you take the alpha A divided by alpha B and divided by the log of the C parameter, that, boom, that's a really big minutes number. By dividing, the number approaching 0 gives infinity. Wow. Okay, so this is interesting. I misinterpreted that. So this would be errors in our deadband. So this could be 5, 4. So if the, so I just wanted to say this would be, I'm just making numbers up. All right, so I think that's what it's saying there is, so this would be our saved run histories, I guess, or saved run, not run of multiple days, but just the same run. So let's pretend that data is sampled every minute during the warm-up. So our temperature delta was 6, then 5, then 4, and it's just simulating the zone starting to meet set point, and then it's barely converging towards the end or whatever. And then so that gives makes our C parameter, our decay rate, calculate like that, and then output our minutes calculation. So kind of interesting. So when we feed in to compute our minutes, I'm still trying to soak this in. There's our deadband, our C parameter, and our errors. So I think I'm starting to kind of understand this. So this, I'm just gonna say this because like when we're passing into this function, it's this is our list. So it's passing in this first value that technically it learned on to compute C. So I'm just gonna say TD today equals, let's just say 7.2. Whoops, 7.2. And then this could be errors yesterday. And I think we could just pass in our number here. All right, so to me this makes more sense that this would be yesterday's data. I'm just going to change this to yesterday's sampling during warm-up. Time delta today, or I'm sorry, temperature delta today. This could be temp delta today. Pass that in. So boom. Okay, that's kind of interesting. I'm just gonna ask AI here. How is this interpretation just to me, like with these, this is helping me understand a little bit. Sometimes the acronyms are just a little bit confusing, but we would basically be learning on yesterday's data. Mismatch is very close. You got the right shape, but there's one subtle mismatch. What you're doing is correctly using yesterday's air decay samples to estimate decay C, using model 4 to project how long it'll take up. One thing to fix what airs yesterday should look like. Model 4, the airs window is per minute. Oh, this is minutes? Okay, I thought this was temperature. All right, so we're learning something. Okay, so all right, so let's get our oh my gosh, so this would be errors. Oh, that doesn't make sense to me. I'm still is your example errors yesterday is not shaped. Model assumes, so C won't have. Alright, hold up. Still soaking this in. One more conceptual. What is temp today? This means at the moment you're deciding optimal start today, set point, but don't interpret it. Each unit will be 7.2. Okay, so slightly confusing. I'm just slightly confused. Like, is the units here supposed to be minutes or degrees? Numbers are degrees. Yeah, okay. Time is implied, yes. Yes, that's how we interpret it. 3 minutes, we're 3 degrees air, so why your example felt confusing. Your sequence looks very linear at first, subtracting, but model 4 expects the data to be with a decay rate. All right, I think we got it right. So it's just saying the real world, the numbers wouldn't look like this. They would be, whatever, 5.8, 4 point something. Like they'd be scrambled a little bit. So whatever. I think we get like what we're doing here. Just like the big takeaway. Deadband is in temperature. This is also in degrees as well. Degrees per minute. Not degrees per minute, but this is minute 1, minute 2, minute 3, minute 4, minute 5, minute 6. Okay, and then this is our temperature delta today. So I think we get the message here. So at least I think I'm ready to move on. And then tomorrow we'll look at day 13. So guardrails and some exponential moving average smoothing. So that's all for today, folks. So thank you for tuning in, and we'll talk to you tomorrow.